here's a quick overview of my senior design project. So I had a couple parts to it. The first part was the particle system, which included transform feedback. The second part had a procedural element in which I implemented the space colonization algorithm. And the third part integrated 3D models into the application. So going over the first part, the physics behind the particle system was that each particle has a mass and its movement is controlled by two elements. The first being the user's mouse, which acted as the gravity center that the particles gravitated towards. The second element was the constant rotational movement, and this was a user-controlled parameter. The second part of the particle system was transform feedback, which is a new feature in WebGL2, and it's a process of capturing primitives generated from vertex processing steps and recording that data into buffer objects. This allows us to preserve the post-transform rendering state of an object and resubmit this data multiple times. For transform feedback, I implemented 3 vertex shaders and 3 fragment shaders. The first vertex shader calculated the physics for each particle, and in the second one, gave the second fragment shader the position, and then that fragment shader determined the color of the particle. And the third vertex shader placed the particle in screen space, and that was what was displayed. And here is what it looks like. The second part of the project was implementing the space colonization algorithm from the Runian's paper. And this algorithm is based off a whole tree structure, and we first have to create the leaves, which serve as attraction points for the branches. Over each iteration, the branches grow closer and closer towards the leaves, and in this way we end up having tree branches that appear to have grown towards an end destination, such as a light source. And the algorithm works as follows. We first define an area for the crown of the tree and populate it with attraction points, also called leaves. Then we grow branches upwards from a starting point, the trunk, until a max distance is reached between the leaf and the branch. And this max distance is a predefined parameter that defines how far a leaf can be to attract a branch. After that, we process each leaf by comparing it to all the branches. For each branch, we check if that is the closest branch to this leaf, and each leaf can only affect one branch at a time. Once the closest branch is determined, we increment the grow count of that branch and add the direction of the leaf to the total direction of the branch. After this, we loop through the branches and process any branch with a grow count greater than 0. Then we get the average direction, create a new branch with this direction linking it to the branch being processed as its parent. Then we reset the grow count and direction of the parent branch. After all of this, we repeat from step 4 until there are no leaves left or no more branches are growing. So at this point, we are able to place the particles in the scene randomly and create a randomly generated tree. And this is what it looks like. Okay, so afterwards, I integrated 3D models into this. So the application would process OBJ files of 3D models and use the vertex positions as the initial positions for the particles. And you can see how this is seen in the rose model and the teapot model. And these 3D models were also integrated into the space colonization algorithm. And how this would work is the vertex positions taken from the OBJ files were used as the initial leaves, the attraction points for the space colonization tree. This would allow the branches to grow into predetermined shapes organically. And here are some examples of what it would look like. The problem that I ran into with this was that running the space colonization algorithm on a lot of particles for every single iteration was incredibly slow. So a solution to this was I would do it only once. So I ran the space colonization algorithm on the entire tree structure and saved the resulting positions into an OBJ file, and that would be loaded in as usual into the application, and particles would just be shown as certain increments at a time. And this is what it ended up looking as. And because we were able to just put in more particles every single time for every single iteration and not have to run the algorithm again, I was able to create growth speed as another user-controlled parameter. And here is the final product.
When the daylight comes